In this video I want to illustrate some of the features in CasaXPS that help to construct a peak model of the form we see here. Let me first explain the different aspects of this peak model that we need to address when we're constructing a peak model. The sample we know to be an aluminium foil that has an oxide layer. So we must have both oxide and metal signal. And when we have an oxide, we might expect the insulating nature of the oxide to produce more void symmetric line shapes. In the case of the metal, we'd expect some sort of asymmetry. And we put these two sets of peaks together, we can see from the data here that there would be some uncertainty in the relationship between the metal and oxide peaks if we develop the peak model based on these data alone. So I will illustrate how to construct a peak model based on data that would be representative of the metal, and then that gives us the opportunity of constructing, with a bit of insight from other materials such as sapphire, a peak model that will represent the oxide and the metal together. The other important aspect of a peak model is the relationship between components within the peak model. And if we know some relationship between these components in terms of area, position or forward half maximum, these are the fitting parameters that we would use to fit the peaks to data. If we know these relationships between peaks, then we can introduce the relationship between these optimization parameters using relational constraints. That means we are relating one of these component peaks to another component peak. And this is really appropriate for a doublet pair. We know that the ratio of these peaks for p orbital ought to be 2 to 1. And we typically know that there's some relationship between the forward half maxima of these two peaks. And in this instance, a very simple heuristic would be to say that we would require the forward half maxima for these oxide peaks to be identical. And this is the type of thing we have to do for an oxide peak because we don't have a lot of information about the separation of these peaks or the forward half maximum of these peaks, but we do need to measure the amount of oxide, and we do need to measure the amount of oxide using components that are in some way conforming to what we would expect for aluminium 2P. Now in the case of the metal, we have a better resolution spectrum. So we have a chance of seeing the relationship between these two component peaks within the metal. So another heuristic when we want to take it from the metal and apply it to the oxide is that if we've calculated a separation for the metal peaks in terms of the doublet peaks, then we might reasonably perhaps apply that offset to both the metal and the oxide peaks. There may be some variation there. If there is, it's well within the uncertainty of any variation that we might calculate for ourselves based on the oxide peaks alone. So we have to make some guess, and the metal will provide a guess for the separation of these two doublet peaks. So the first question is, how would we construct a peak model for a metal peak given data such as these? Well, we'd rather not is the answer to that question. What we'd rather do is look at data that happens to include signal that is mostly metal signal. And that's exactly what these data are. They've been measured from an aluminium foil that has been sputtered with an ion beam to remove both the carbon and the oxygen. So we now have a spectrum that ought to represent the metallic form of aluminium 2P photoemission. What we see here are two peaks, and these two peaks are the basis for the previous peak model. So they are fully constrained to make sure that these two peaks are now related to one another and represent, through these constraints, the metallic aluminium 2P signal. Let's have a look at what the aluminium 2P signal looks like from a metal, and here it is. So this is the peak model for the metal that is now constrained in a format that will be suitable for use with the previous data. We can see from the components property page that we have a set of relational constraints, and these represent a relationship that has been established based on a given line shape. This is an asymmetric line shape that was developed based on these data, and having developed a line shape that represents the metallic signal using relational constraints in terms of area, so we are forcing a 2-to-1 relationship between these two components, and also forcing a forward half maximum constraint that the relationship between both of these peaks, they both must have the same forward half maximum. Now, before the positional constraint was introduced, this was allowed to adjust within an interval, and on the basis of the line shapes and these two constraints that can be assumed, perhaps, I always have an element of doubt, there may be some reason why the forward half maximum does differ. For example, titanium 2p, titanium 2p doublet, the two peaks, they do not have the same forward half maximum. So it's not a golden rule that all peaks ought to have the same forward half maximum. But when we're dealing with data such as these, it's a reasonable approximation, especially when we want to work out what is the relationship in terms of position, the relative position of these two peaks. So fitting these peaks to these data without any positional constraints, this allowed a positional constraint to be established that can be used in the other peak model. So we're making use of this aluminium 2p metallic doublet to try and establish the relationship that we would like to see between the doublet pair. And we can apply that with a little bit of variation to a peak that has been measured after the sample has oxidized a little bit, and so we have an oxide peak and we have the metal peak, and these are all the constraints that are now visible as part of a table that is added to the data using the annotation dialog window, and that would be using the components property page on that window. This annotation is showing only the constraints, so that would require the use of the option that says include constraints, and then excluding all of these other factors other than the line shape, the forward half maximum itself, or the area, or the percentage. These can all be excluded or included in the table based on these tick boxes. So they've been arranged to produce this table over the data showing the constraints that we also see in the components property page. But we can now, using a display option on the colors property page that says mark component forward half maximum, and when I do that, that is to say enable the display of these markers, you can also include over the data the different relationships between the optimization parameters. So we once again can see that the position, the area and the forward half maximum of the green peak now relates to this red peak, and there's a similar relationship between these two peaks representing the oxide, that there are relational constraints making sure that the oxide doublet is conforming, with the exception of the line shapes. The line shapes are different, but we are making use of the identical constraints between these two metal peaks applied to the oxide. You can argue whether that is actually appropriate or not, and maybe you could do some further refinement of the peak model, but when constructed in this way and then applied to these other data where the oxide is indeed, let's just update the display. So the oxide is constrained as described previously, the metal is constrained as described previously, and here we have the peak model fitted to the data, and we could just fit this to the entire set of oxide peaks that were measured as part of an iteration over this sample. So we can go through and test the peak model against multiple data, and we see that pretty much across this entire sequence of measurements, all independent, so we get different data in each case, and we're still getting a decent fit based on this peak model. So applying these constraints, working out the appropriate line shapes, and being able to see the relationship between constraints as we examine the data and these peaks within the peak model. This is all useful when we're trying to understand XPS data by modeling with component peaks the chemical state of a sample.